Okay, mountains were now really old, but how were they formed? Another significant shift in thinking about mountains occurred in the first decades of the 20th century. In 1912, a German meteorologist named Alfred Wegner stood up in front of an audience of eminent geologists in Frankfurt, and he told them that the continents move. And if that wasn't startling enough, he went on to tell the incredulous audience that 300 million years ago, the continents were all part of a supercontinent, a single supercontinent, Pangaea, meaning all lands. For proof, Wagner said, take a look at the globe. Look at the dispersal of the continents. Move them around a bit and you'll see that they fit together like a jigsaw puzzle. He had harder proof too, such as comparative fossil specimens and climatic evidence. But whatever the case, like Thomas Burnet in the late 1600s, Wagner was arguing against the prevailing ideas of the day, and the opposition to his theory was both immediate and noisy. It wouldn't be until the 1950s, with advances in paleomagnetism, the study of the Earth's magnetic field, that his theory of continental drift was reappraised. Today, Wagner's theory is the substantial basis for our understanding of plate tectonics and for the formation of mountains. The basis of plate tectonics is the idea that the Earth's surface is broken into several rigid plates. These plates are made up of the Earth's crust and the upper part of the mantle layer underneath. Together, the crust and the upper mantle are called the lithosphere. Plates glide on the more ductile asthenosphere, which is also part of the planet's more malleable inner layer, the mantle. It's the mantle that encases the planet's blazing hot core. The lithospheric plates are comprised of either continental or oceanic crust, or both. Ocean plates are thinner, often less than 100 kilometers thick, but denser than the continental plates, which are roughly 150 to 200 kilometers thick. Each plate is moving in various directions at rates from 1 to 10 centimeters per year, and that's as fast as fingernails grow. The driving force behind this slow, relentless movement is the convection in the mantle. Hot material near the Earth's core rises, and cold mantle rock sinks. So you can think of this as a pot boiling on the stove. It's a slow churning that's been jostling the Earth's crust around, arranging and rearranging its surface since the very beginning of the planet. Where the plates pull apart, new volcanic material fills the void, as at oceanic spreading ridges or at continental rift zones. Hot magma wells up at these divergent plate boundaries, forming new crust and further shoving the plates apart. The largest and best-known undersea mountain range is perhaps the Mid-Atlantic Ridge, which extends north-south for several thousand kilometers, roughly parallel to the coastlines of Europe, Africa, and the Americas. The active volcanic island of Iceland is the ridge's highest expression, where it protrudes spectacularly above the sea level. An example of an active continental rift zone is the East African Rift. Here, the African plate is actually in the process of splitting in two, and as extension continues, lithospheric rupture will soon occur. The Somalian plate will break off, and a new ocean basin will form. Of course, I mean soon in a geological sense, so don't panic. From this map of East Africa, note the positioning of the region's historically active volcanoes to the actual rift zone. Among them are Mount Kilimanjaro and Mount Kenya, the highest mountains on the African continent. Okay, that's what happens when plates diverge, but what about when they collide? The nature of convergent plate boundaries really depends on the type of plates colliding. Where an ocean plate collides with a continental plate, the denser ocean plate is pushed or subducted beneath the more buoyant continental plate and is inevitably absorbed back into the hot inner Earth. Along these subduction zones, melted rock formed by subducting ocean crust can find its way to the surface, erupting and building volcanoes along the plate margins. Much of the Pacific Ocean boundary is surrounded by long stretches of volcanoes caused by this type of tectonic collision. This particular boundary is known collectively as the Pacific Ring of Fire. On the other hand, if you have two continental plates colliding, it's not as easy for one plate to subduct beneath another. The resulting collision can form the largest of mountain ranges, and a great example is the Himalaya, where the Indian subcontinent is moving north into the Eurasian plate. As you can probably imagine, collision zones are the most seismically active areas on the planet and produce 90% of the world's earthquakes. A third type of plate boundary is known as a transform margin. Transform margins mark the slip-sliding plates, such as California's famous San Andreas Fault, where the North American and the Pacific plates grind past each other in a mostly horizontal motion. Although the forces aren't as great here, these boundaries can still give rise to mountains on occasion, such as the San Gabriel Mountains of Southern California. Let's do a quick review of what we've just learned. A convergent plate boundary is where plates are slamming into one another. A divergent plate boundary is where plates are pulling apart, as at continental rift zones or at oceanic spreading ridges. The outer crust, the plates themselves, whether it's continental crust or oceanic crust, is what's referred to as the lithosphere. And the lithosphere sits upon the asthenosphere, that ductile portion of the upper mantle where the whole process of plate movement is driven by the convection of hot plastic rock. It's here where a diving subducting plate is absorbed back into the inner earth.